Hello, today I'm going to tell you about compositional symbolic execution. So let's write that down here at the top. Oops. Okay. So we kind of have two parts to it. We have the compositional part and we have the symbolic execution part. So let's start with symbolic execution. So as an example, I think it's best to just start with examples right away. So let's create this Rust function that takes an integer and it's just going to double it. So that's our function. And we have a couple of different we have a couple of different ways we can execute this. So the concrete execution would take, for example, the number 2, and it will return 4. We also have abstract execution, like if some of you have heard of abstract interpretation, where we can take some abstract representation of a number. For example, we can take the abstraction of odd numbers. If we double an odd number, we get an even number. And now symbolic execution is, you could say, even more abstract than that, because it just takes some symbol, some symbolic variable, we call it, or symbolic value, we'll see later. We don't have to, we can put whatever in there, we don't have to put just x. But if we put just the symbolic variable x, we get 2x back. So it's as simple as that. It's basically just putting in a symbol, and in the operational semantics, instead of saying, 2 times an integer will give you this integer, we just say 2 times something is a normal form, essentially, and we don't reduce it further. So we get 2x. So that's quite simple. Now we can also generalize this to say that for all x double x is equal to x, right? We could say something like that. We'll see in a second that that's not quite right. You might already have some idea why that might not be quite right, but we'll get back to that. Let's take another example. So we have the function is even, and it's going to also take an x, and this time it's going to return a boolean. So we're just going to do an if statement. If x, we'll just use pseudocode here. If x mod 2 is 0, if it's even, then we return true. Otherwise, we return false. Okay, we can obviously, you can simplify this code, but I'm just writing it here just so you can see, just to prove a point, essentially. So just go along with me for a sec here. And so now we would also like to say, like, what happens for any x, right? So let's take this as a starting point, and we're going to have for all x is even x. Well, what should this be? We're going to want, can I do cases here? We'll see. Is that a math mode even? I'm not sure. Does that work? Yeah, seems to work. Okay. So we're gonna have true if x even. operate with this in text. And then we're going to have false otherwise, right? Right, so this didn't quite work. The underscore didn't work. Let's just wrap this in some text. Oops, it didn't like that. Too many T's. Yeah. Okay, so there's a specification. So we can do it like that. Now, we kind of starting to see a pattern here. We can generalize this actually and turn this into a table. We can do result here, and we can do path condition here, right? Because the reason we get this branching is because of some paths that were taken. And that's kind of like the key result, well, the key thing of symbolic execution. You have a result, and this can be actually generalized to the symbolic state. We'll get onto that in a second. And then we have a path condition. So essentially, the key insight is that symbolic execution groups values by the path they take. So we basically have a grouping of x's into even x's and into odd x's. Right? Let's look at another example because I want to kind of prove a point in a sec. So if you go back to this function over here, right, we can do the same thing. So I'm going to start using different notation now. Okay. So we're going to have x even here, x odd here. Okay, so we have result path condition again. No, this time it's the other way around. Have a path condition and a result. Let's try and do the same thing for this example up here. So actually this is kind of a lie, this specification over here. That is not correct actually. So let's cross that out. What we actually have is we have if x is less than or equal to U32 max divided by 2, I believe, then the result will indeed be 2x. But if it's greater than half of max U32, then we will get an integer overflow, right? We're going to get an error. So integer overflow. And to differentiate between the error and the OK cases, we'll just put OK and error here. Just be the other way around. Right, so we kind of see, now we actually do see, like if we have arithmetic overflow detection enabled in Rust, then essentially the program will take two different paths. Either it will continue with the value 2x, or it's just going to crash, it's just going to panic with an integer overflow. So those are two different paths the program can take. And obviously this error will propagate up. So if you do anything on an error state, you just get the same error state. Whereas the value 2x, that can be used for further computation. So yeah, so the paths here, the paths were the same as this like odd even example, but here, like the path conditions, but here the path conditions were clearly different. So we have these paths, right? So you can imagine we can build more complex analyses. And we're going to get a lot of paths, right? So let's do an example. We're gonna write another version of is even over here, right? So we're gonna do something like this. If x mod 2 is equal to 1 now, we're gonna return false. Otherwise, we're gonna return true. Okay, and if we do the same analysis that we did over here, right? Well, let's actually, here we were a bit abstract. Here, let's actually have it just as we did before. Okay, so, sorry, not as we did before. We're gonna put down exactly this. Okay, so in one path, x mod 2 is equal to 0. And then we're just going to go straight to the other path. So we just AND these conditions together. And we're going to get, and we're going to AND it with this. So that's one path. The other path is obviously if the second condition does not hold. And then the third path is if the first condition doesn't hold, right? Just gonna make this a bit nicer. It doesn't matter. So we have 3 different possible paths, in theory, right? If we just have a naive kind of algorithm, it's gonna find 3 paths. Now, what happens? Like, we can obviously see that one of these paths is not going to be reachable, and that's just because we wrote some bad code. But like in practice, you can kind of imagine that, for example, this integer overflow path might not be reachable because we only ever give it like smaller numbers, say. So what we can do is we actually use SAT solvers to see if path conditions are satisfiable. So can it be the case that x can both be even and odd? Well, no, it can't. So we're gonna actually prune this. So I got this the wrong way around, didn't I? This should be false, and this should be true. So we're going to actually prune this first path because we know it's not actually reachable. Okay, so we have 1 path less in our analysis now because we basically said this path is not satisfiable. There's no reason to keep analyzing it. So yeah, like in practice tools, we use SATs or SMT solvers, which are basically more fancy SAT solvers. So a couple of uses of symbolic execution. I actually haven't finished noting this down, but we can do testing. We can basically write tests. Instead of using concrete numbers, we would use symbolic values, and then we would do assertions on these symbolic values. So for example, I can assert that if I give it an x that is less than or equal to this, I will get 2x, right? I can test my code like that. And we can also do verification with symbolic testing. So that's like the cooler part. And now you might see a problem here that we're going to get a lot of these paths, right? And it might be hard to scale the analysis. So what we can do is, well, we can introduce the compositional part again. And the compositionality basically is composing symbolic execution with function specifications or function summaries. So what language should we use for our function specifications? Well, why don't we use separation logic, right? We know how to create function summaries for separation logic. So let's do that. What is the advantage of using separation logic for function summaries? Well, separation logic is very popular, so every tool should be able to support it, and therefore it's a language that is cross-tool compatible. So it's kind of as far as I have for this first part, and we'll resume in a second once I've figured out what to do for the compositional part.